when at first my.
When you're in a circular motion.
Wait, say that again?
When should you use static friction and kinetic friction when you are in a circular motion? So like, do you use static only when you're in the path of the circular motion, and then the kinetic when you're drifting away from the circular motion? Does that make sense?
If you're going around a bank of a curve and you don't want to slide up or down,
Yeah.
you'd be using static. Once you start sliding, you would use kinetic, but I usually just, yeah, once there is sliding going on, it is kinetic friction. I'm not quite sure how to really, is there a specific case you're thinking about?
There's one of the tests where it was like, I'll pull it up real quick. This one, short answer number 5, question A.
Flat constant speed.
So it's not just only static when it's skidding, it's static, but
Well, the first one, he wants to go without skidding.
so that's gonna be static friction.
That would be static.
But if it says what's the speed when it starts skidding, it's kinetic.
The speed at which he would start to skid would be close enough to the speed, the greatest speed where he's not skidding. So you can still use static. You're at an extreme. So you're trying to figure out the speed at which he would hit that breaking point, that maximum static. So you can still use static. Does that, I'm not sure I answered your question or not.
It somewhat solves it. Well, like, I was just confused because I don't know when to use static or kinetic when I was solving the circular motion problems. Like, because it's already in motion, so I don't know why I have to use a static motion if it's already moving around a circular motion.
It's a question of whether it's sliding or skidding. That the wheel, in a nice ideal situation, the friction between the wheel and the road is static. Even though the wheel is moving, but there's not sliding going on. So you would still use static there too.
Okay.
Yes, kinetic friction is not an issue of whether it moves or not, it's whether there's rubbing or not. And ideally, a car just touches, doesn't rub. Now, reality is, yeah, there's gonna be a certain amount of, well, that's what they lump in rolling friction. Because you have a certain amount of static and kinetic both involved. But we have the convenience of making it a little bit more ideal than that. Still seems like you're not satisfied with the answer, but.
Well, I'm just trying to ponder on it. Like, I'm trying to like really, think about it in my own definitions that I remember on the test.
Okay. I'm trying to think if I've done any circular motion problem where you have to use kinetic. I don't think I have.
So we won't have a circular motion kinetic friction problem on the test.
Odds are against it, unless I suddenly get inspired by what Robin has said. And
Please don't. I got too much problems now.
I think only once, there probably might be more than once, but there was a force diagram problem years ago that was inspired by a student who speculated. He was wondering about the forces involved as I was pushing a cart loaded with stuff. And so I spent the next couple of days sort of analyzing that, and then I thought, oh, this is gonna make a problem.
How do people do on that problem?
As well as they usually do with force diagram problems.
What is that?
Some understand it and some don't. It's a spread. Questions? Other questions? All right. It seems like we last left off with something. We did the hit in the spring. That was the last thing we did, right? Okay. We have, in essence, there's just not time. We have, in essence, done energy. I want to talk about momentum, and then we will return back to energy. So we're going to start out, so this is the chapter, whatever the next chapter is. 8. The trouble is, you need to know energy and momentum in order to talk about collisions really in proper detail. So now we cover the basics of momentum. Newton's close. One of those is going to hit. Oh, it's like this here. All right, so Newton's third law. I have two objects interacting with each other. They exert an equal magnitude of force, opposite directions. That's the minus sign. And they touch each other or interact with each other for the same amount of time. So what I'm going to do is I'm going to multiply this by the amount of time. What does F equal?
MA.
This is the force on object A by B. So the first letter is the receiver of the force, the second is the source. So this is the mass of A times the acceleration of A times the amount of time that the two objects were interacting minus the mass of B times the acceleration of B times time. What is acceleration times time?
Velocity. Wait, no.
Not quite.
Speed.
Worse. No.
Displacement.
Robin was close. So far, Robin was the closest with his first answer. Unless I misheard.
Average velocity?
No.
Instantaneous velocity. Instantaneous velocity.
No, instantaneous is implied.
Average acceleration?
That average was already said. What'd you say?
I said average acceleration.
Well, acceleration times time is not average acceleration. All right. What's the formula for acceleration?
Change in velocity over change in time.
So what's acceleration times time?
Change in velocity.
Yes, change. It's not the actual velocity itself, it's the change, and that's rather critical here. So we have the mass of A times the change in velocity of A is equal to the negative mass of B times the change in velocity of B. When you're finding change, how do you do it?
Initial, or final minus initial.
Yeah. So we have MA times VA initial no, final minus VA initial is equal to negative mass of V final minus V initial. The vector symbols are still there because we are dealing with vector quantities. I'm now going to distribute. So I have mass of A M sub A V sub A final minus mass of A V sub A initial is equal to negative mass of B V sub B final plus mass of B V sub B initial. Now I'm going to get all the initial terms on one side and the final terms on the other. And so that means bringing this over to the right-hand side, that over to the left-hand side. So I have mass A, V, A final, plus mass B, V, B final, equals mass A, V, A initial, plus mass B, V, B initial. At this point, if not sooner, physicists get really tired of writing. They think, NV showing up 4 times, let's just come up with a shorthand for that. So they figured the letter P. So they'll just let P is equal to mass times velocity. And so this just becomes P A final minus P plus P B final equals P A initial plus P B initial. Now at this point, the physicist's heart gets all aflutter, and that is a P there. Because what we have here, whatever P is, my total initial value is equal to my total final value. In physics, this is known as a conservation law. Therefore, you have to, of course, come up with a word for it. And this is momentum. And this is a sort of quick and dirty derivation of conservation of momentum. So if I have 2 objects interacting with each other, the total momentum should be conserved. So whatever I start with is whatever I end with. In terms of one other bit of notation, typically you use a lowercase p if you're talking about an individual momentum, and a capital P if you're talking about the total. So sometimes this will be written as P initial equals P final. Now my capital P's and lowercase p's will potentially slightly different, but not every time I write it. So I'm not necessarily, I sometimes will abide by it, sometimes I won't, just because it's just difficult in the context of a board to differentiate between capital and lowercase p's. Questions up to here?
Is there a difference in the bottom P's and the ones on top? Those are the bigger ones, and the smaller P's are different?
Yeah, these are the small p's. Those are the ones for an individual object. This is total momentum of a system. So let's just start out with a nice simple problem. Unless there's another question.
Can you re-say what you just said about what the little p's are versus what the big p's are?
The little p, it would be the momentum of an object. Big P is the momentum of a system. If I have a 3 kilogram mass going 4 meters per second, what is its momentum? The subscript I'm gonna use is one related to the mass, so it's a 3 kilogram mass. So that's why I have a piece of 3 there. If you'd rather do A or 1 or something like that, go for it. What is the momentum of this mass?
3 times 12 newtons? Is it going to be
Wait.
12? So since that's mass times velocity, it's 3 times 4.
Okay,
So it's gonna be 12 some
Okay.
units.
what are the units?
Kilograms. No, I'm not sure.
Ooh, it's disease. Too many pers.
Kilograms, meters, percent.
There. It's the kilogram meter per second. Ah, that old chestnut.
So the
Yes.
reason we got there is because we took the second half of the equation up there, the NAVAI plus NB, and the NB is just 0 because of the, no,
I don't have a second mass.
okay, wait, there's no second max, so it's just,
Sorry, Naya?
you're good.
Okay. Now, this units here, kilogram meters per second, sort of a nuisance to write. They have not yet come by and honored anyone in particular by coming up with a 1-word unit for it. So if we notice over here, I don't switch sides until we get to this step. This is this step right here, I've now switched sides. So until that step, everything on the left-hand side here is equal. So I have this is equal to this. So I have the force on A from object B times time is equal to, well, using our P language over there, this is P final minus P initial. This is just the change in P for object A. Typically, the subscripts are dropped, and you're just supposed to know. So the units of this should be the same units as that. If they're equal, the units should match. Excuse me. Well, if units of this is a kilogram meter per second, this should be equal to a Newton second. And it is. A Newton, if you recall, is a kilogram meters per second squared times seconds. That will cancel out, and I'm left with this. So, alternatively, its momentum so this is also equal to 12 Newton seconds. Alternatively, you could create your own unit. Now, it does have the plus side of the fact that if you just have to define it somewhere on the paper or on the board, and it's good to go as long as it's still there. Or, and then you only have to use a single letter. Alternatively, the downside of it is you do have to define it every time. So on a test, if you write it on the first page, that covers the whole test. We'll call it in computer science a global variable. Or if you do it for a particular problem, a local variable. The one that I will sometimes use is the Descartes. And I will define a Descartes as a kilogram meter per second. It only has meaning as long as it's written there. So if I use Descartes over on the marker board, and then erase this first, suddenly that's invalid. Matter of fact, since I'll probably go to another page at some point on this, I should write it over here so it has a little bit more permanence. Since this is the unit I made up, you don't have to use it. If you wish to honor yourself and use some letter from your name, please do not pick a letter that is already being used. Nayeli cannot use a capital N because capital N is already being used for Newtons. Sorry.
It's okay, so that means I just can't use anything in my name, that's okay.
Trying to think of some letter that is in your name that, in terms of units, I don't think I is used in any unit.
Initial,
That's a subscript.
well, that would still be confusing.
Yeah, it would be. Anyway. So if that is defined, I can also write 12-bit cards. Questions up to here before I make it slightly more complicated. All right, I now have a 5 kilogram mass going to the left at 2 meters per second. What is the momentum of this object? They're gonna collide into each other, by the way, but they haven't done it yet.
Negative 10 newtons times seconds.
Say that units again?
Kilograms times meters divided by seconds. I was
Okay.
saying the second one that we derived. But that could work too.
I missed some of what you just said.
What I was saying is I was trying to get the newtons times seconds, but the
Oh.
first one could work too.
And I was, so kudos for not making the common mistake. The common mistake is say, oh, it's 5 times 2 is 10. No, once it was established that this was positive, things going in the opposite direction are negative. So this is the initial. What is my total initial momentum? It is simpler than you think. If
Two.
you are, pardon?
2
Yeah, keep going.
2 newtons times seconds.
Now, as before, putting the dot in between the units like this is proper